right then, we are going to move on to, and did you guys get a chance to watch the video for 4.2a? If you forgot about it, it's okay. You can still get caught up on that. We are going to be doing some we're going to be doing some stuff on pH today, but it will be good to go back and watch through that because it sort of gives you the big picture of pH. Whereas today we're doing like all the little bitty details of pH, okay? So today, 4.2b, which you just picked up. Hello, I pressed yes. No, you're not believing my finger has any sort of say. There we go. All right. And unfortunately, I think I labeled it 4.2a at the top, so you can cross that out. And that is 4.2b, the relation between hydrogen, hydroxide, pH, pOH, Kw, pKw. And some of this you know already from 4.2a, but we're going to really focus in on the math part. Oh, and by the way, I have marked your tests. I will be putting up the marks after school today. I'll be posting them on my ed. So if you want to check your mark, I've still got a few people writing, so I'm not going to give them back yet. But yeah, they're there. Okay. Chemists, being a lazy breed, are always looking for shortcuts to writing things down. Like me, MC for molecule, RXN for reaction. So instead of having to write these powers of 10 when dealing with a hydrogen or hydronium concentration, they were looking for a shortcut because most of your concentrations of hydrogen are little bitty concentrations that are like, 3.2 times 10 to the minus 5. That's a lot of writing, yes? How could we simplify this? Well, a mathematician suggested that we use a mathematical device called a logarithm. How many of you are familiar with logarithms? Excellent, most of you. If you are not, fear not. You just need to be able to press the log button on your calculator for chemistry. Okay, so if you can do that, you can do logs in chemistry. However, we are going to go through just a very little bit about what a log actually is in the very simplest way possible. So if we take the logarithm, or in other words, the log of 1 times 10 to the minus 5, we get minus 5. Yes? If we take then, by the same logic, if we take the log of 10 to the 7, what would we get? 7. And what if we took the log of 10 to the negative 3, we would get, everybody, minus 3. And if we take the log of 1 times 10 to the minus 4, we get, or sorry, not minus 4, 1 times 10 to the 4, we get 4. Okay, so that's what a log is basically you take you're finding the power of 10 is really what you're doing, okay? Now, this is all very well and good as long as we have that part of the number is a 1, okay? We can do it in our head. However, if the power of 10 is multiplied by something other than 1, you will be wanting to use your calculator unless you are far, far smarter than I am. So, let's say you wanted to find the log of 5 times 10 to the negative 5. Could you please plug that into your calculator and see what you get? And if you don't know how to use your calculator for this, call me over. I can help you out. you should, hopefully, get negative 4.3. Anyone need a hand finding that? Okay. And this is actually because you could, in theory, rewrite the number 5 times 10 to the negative 5 as 1 times 10 to the negative 4.3. I didn't make that box big enough, but anyway. That's weird, yes, but that's what it means. Now the chemist said, hey, this is pretty good. I got rid of all the times 10 to the nonsense. But because concentrations tend to be very small, we're still stuck with all these negative signs, yes, because our powers of 10 generally are times 10 to the negative something because concentrations are small. So in order to eliminate this, they thought, okay, let us take the negative of the logarithm, which will just change the sign for us. So all our negatives will then become positive. So, therefore, pH, we don't just take the log of the hydrogen ion concentration, we take the negative of the log of the hydrogen ion concentration. There's another way we can write this if we wish to. What could we put instead of concentration of H+? What can we use in place of H+? There's something else that essentially means the same thing. Pardon me? Proton, yes, we could. There's another chemical species, H3O. Yep. So if you're not used to it yet, which maybe you're not because we haven't been doing it very long, get used to the fact that hydrogen is the same as hydronium. Yes, the two are equivalent. They are the same thing. Hydrogen is how we write it, like in short form. In reality, anytime you put hydrogen in water, what does it do? It attaches to something. What does it attach to? Yes, the water molecule. Becoming H3O plus, and tell your partner what the name of that ion is. Hydronium. So I'm going to just try and swap the two in and out, just so you get used to seeing like one being the same as the other. Hydrogen and hydronium can be used interchangeably. All right, so let's say that we wanted to find the pH of a solution where our hydronium ion concentration is 3 times 10 to the negative 3. So we are going to take the negative log of 3.0 times 10 to the negative 3. And we get, you try it too. we get 2.52. Now this is the part of pH which is maybe the most confusing for people, and that is the significant figures, okay? How many significant figures do we have in 3.0 times 10 to the minus 3? We have 2 sig figs. It turns out that in any sort of logarithmic number, only numbers after the decimal are significant. Oops, I did not leave myself enough room. It's easier to understand that if we take a look at a number where we have 1 as our coefficient. I don't know if that's what you call it. So let's say we had 1.0 times 10 to the negative 3. Yes? If we take the negative log of 1.0 times 10 to the negative 3, we get, and could you guys tell me what we get without using your calculator? Yeah, you get positive 3 because it's the opposite of negative 3, right? So we get positive 3. Now, where did this 3 come from? Came from, ooh, what happened? I erased as well. Came from up there, yes? That is our power of 10. Is our power of 10 a sig fig? Do we count that when we count our significant figures? No. So that is not a sig fig. So that means that this 3 is not a sig fig, which means that this 3 is not a sig fig. So how will we, in our answer, make sure that we have 2 significant figures? What will we have to write it as? Yes? 3.00, and those are 2 sig figs. Okie dokie. And even though it's not so obvious when we're dealing with things that don't have that lovely number 1 in front of our power of 10, the principle works the same way. Okay? All right. I don't know why I made these boxes so small. They should be bigger, but maybe I just shouldn't have put boxes at all. Anyway, we're going to find the pH for the following solutions. The first thing you're going to do, because you need to memorize the formula for pH, you might as well write the formula for pH every time you do this. Yes? Also, because if it's a written response question, you get marks for writing pH equals negative log of hydrogen. That right there is worth 0.5 marks. Yes? You don't write it on a written response question, you don't get that half mark. So you would write that, and then you would write negative log of whatever it is you have, 5.4 times 10 to the negative 12. And like I said, I made these boxes way too small. Silly of me. Why did I put a box even? Why didn't I just leave it open? Anyway, it doesn't matter. So you guys are going to go through and do the rest of the examples, and then I'm going to write them down with just random numbers of sig figs, or sorry, not sig figs, digits, and then we're going to look at the sig figs together. So once you're done, you can check your answers with mine, bearing in mind that I do not have the correct sig figs here yet. Okay, so for our first one, how many significant figures are in our hydrogen ion concentration? 2. Thank you for answering, everyone. I really appreciate it. That's awesome. Now, where would those 2 sig figs occur in my number? After the decimal, thank you. They would happen after the decimal, so it's going to be right there. So that then is going to round to 11.27. Same thing for our next one. We still have 2 here, so we're going to round to 6.27. Yes? And I want you to notice that we have the same coefficient here. I don't know if those are called coefficients. That's what I'm going to call it, the thing in front of the times 10 to the whatever. Do you guys know if there's a name for them? Okay, you don't know either? Okay, we'll call it the coefficient, okay? The coefficient is the same. What do you notice about the pHs that are the same? Everything after the decimal, which should make sense, yes, because the stuff in front of the decimal is the power of 10, yes? And you'll notice, okay, this is a 12, that's an 11, but that's because it's not like 1 times 10 to the negative 12, and if you don't feel really awesome about that, that's okay, just let your calculator do it for you. I don't feel awesome about it either, but I just go, yeah, that's all good. And here we have 10 to the negative 7, so that's why we have a 6 instead of an 11 there. Yep, but then the rest of it corresponds to this bit here, and that's why our significant figures are only after the decimal. All right, our next one. How many sig figs should we have? 3. So where am I going to round my number to? 1 point what? 1.1, everybody? 76. Yes, very good. Okay. And then finally, 2 sig figs. So this is then going to round to 16.72, 2 sig figs. Now, remember last day we looked at our pH scale, and normally when we see a pH scale, it goes from 0 to 14. But hopefully, did I mention it with this class? You can go below 0 and you can go above 14. Yes? And you can see that we did that here. So, but in order to go below 0, oops, I dropped my negative sign there. That should be negative 1.76. In order to go below 0, your concentration of hydrogen has to be really high. 15 molar is a really concentrated solution. Okay? So for pH to go below 0, concentration of H plus must be very high. Similarly, you can see here we've gone above 14. Yes? But what is our hydrogen ion concentration like? It is really, really, really itty bitty. It's small, okay? For pH to go above 14, concentration of hydrogen must be very small. Stop jumping around on me, you silly screen. There we go. I should have left more space. That's okay. Next year. The autoionization of water. Auto, meaning something one does to oneself. Ionization, turning into ions. So it turns out that water, pure water, just hanging out on its own, actually dissociates to a very, very small degree. only a tiny amount of H2O is ionized. Most of it is just H2O together. Conductivity apparatus, have you seen one? Maybe, maybe not. Basically just something that says, is it conducting or not? And one way to do that is if something will conduct electricity, the light bulb will light up. And we're going to start with some plain old water. Does water conduct electricity? You know? Fresh water, it ought not to conduct electricity. Let me make sure this thing is actually on. There we go, that's on. Let's watch. Ooh, look, nothing happens. Yes? And that's because the amount of water that actually dissociates into H plus and OH minus is so small, okay? It's like 10 to the negative 7 molar, okay? So like hardly anything. Just because it's a shame to bring this out just to show you that water does nothing, I'm just gonna grab a little acid and base. Okay, so we have here, let's see, what have we got? 0.1 molar HCl, 1 molar HCl. Okay, so let's do some 0.1 molar hydrochloric acid. 0.1 molar, 0.1 molar. How much molar? 0.1 hydrochloric acid. Okay, yes? What kind of an acid is hydrochloric acid? Strong. That's why you get such a bright light, even though the concentration is not so great. Now let's try the 1 molar. See if it's any different. Is that brighter? It's hard to tell, right? You would really, if you really wanted to do it quantitatively, you would use a voltmeter instead of a light bulb, yes? Okay. And let's see. Oh, I got some acetic acid, CH3COOH. What kind of an acid is acetic acid? Is it a strong acid? Acetic acid is vinegar, if that's helpful. Is it a strong acid? No, because we don't usually want to eat strong acids. Yes, and I'm happy to sprinkle vinegar all over my, potatoes, and stuff like that, but I would not want to do that with hydrochloric acid. Yes, that would be nasty. So let's check this out. We have a weak acid here. Oh, and this is 1 molar. Yes, so it's dimmer than the 0.1 molar strong acid because most of the CH3COOH stays together and only a little bit dissociates. And now let's try the 0.1 molar acetic acid. This one should be very dim. If I shake it around a little bit, it kind of gets going, but you can see hardly anything there. Once again, let's just compare that with our 0.1 molar hydrochloric acid. Whoa! Yes, that's the difference between a strong acid and a weak acid. Do we need to see a base or are we okay? It'll just light up. It's just the same. Okay. I could just pretend one of these is a base and stick it under there for you. You wouldn't know that. It's a base. Okay. And I will unplug this because otherwise I stand a good chance of electrocuting myself. Which is not so fun. All right. So, water does not ionize enough to conduct electricity. It ionizes a tiny bit, but not enough to do anything really substantial in terms of conducting. Now, in reality, water doesn't actually just split apart into H and OH. In reality, water acts as a Bronsted-Lowry acid, and it also acts as a Bronsted-Lowry base. And what does it mean if it can act as a Bronsted-Lowry acid and a Bronsted-Lowry base? It is amphiprotic. So let's look at what that would look like. Like I said, these boxes are killing me. They're way too small. So I'm going to write little skinny letters as much as I can. H2O, liquid, plus another H2O, liquid. And we're going to have a hydrogen move from one water to the other water. So this one's going to act as an acid. This one is going to act as a base. And that means that that first water, instead of being H2O, will now be H3O plus aqueous plus, and that water that gave away a hydrogen, all it has left then is an OH. So that's what happens in reality. The other one is the shorthand method. But from these equations, we can write KEQ expressions. So let's write two different KEQ expressions for the autoionization of water. What are the products? Let's do this one first, top one first. What are the products there? H plus and OH minus. Okay, so we have H plus times OH minus. Now, what's going to go in the numerator? Nothing, because water is a liquid. Okay, so that's it. And we could also write it another way. And in fact, before we do, this is actually known as, it's got its own special little letter, KW. And it is the constant, the equilibrium constant for the autoionization of water. Constant has an S in it. How else could we write kW? Instead of writing it as H plus times OH minus? Yeah, we could use H3O. Yeah, exactly. Times OH minus. And if you're ever wondering what the value is for this thing, it is 1 times 10 to the negative 14. Not too hard to remember if you remember that the usual pH scale goes from 0 to 14. And so kW is 1 times 10 to the negative 14. But if you forget, it is on your data booklet. Let's go look at our data booklet. Here we go. Down at the very, very bottom, right before we hit the strong base area, you can see that we have water dissociating into H plus and OH minus. That is our autoionization of water. And the value is given to us, 1.0 times 10 to the negative 14. And that is our kW. Now you'll notice that this kW is in the same column as all the Kas, and in fact it is the Ka for water. Okay, so kW is a special, it gets its own name because we use it so frequently, because we will use it to actually convert between, if we know a hydrogen ion concentration, we can calculate hydroxide. If we know hydroxide, we can calculate hydrogen. We use it all the time, so it gets its own little name, kW. But it really is just a Ka for water. Oh. So super useful, this kW. So if I give you a hydronium ion concentration like this one, 3.0 times 10 to the minus 3, we can use our kW equation. What is our kW equation? kW is equal to concentration of hydrogen times the concentration of OH minus. We're writing it down because you need to be able to write this down, right? This needs to be a memorized formula. And kW, what is the value for kW? What is the number? Sorry, yes? 1.0 times 10 to the negative 14. Excellent. Could we rearrange this formula to solve for OH minus? Yep, what would we get? What would be on the top? kW. And on the bottom, H plus. And once you have that, kW is a known value. It is 1.0 times 10 to the negative 14. And we know that the hydronium ion is the same as the hydrogen ion, okay? And so we can just plug that in, 3.0 times 10 to the minus 3, and we get 3.3 times 10 to the negative 12. Is that answer missing anything? Units. It's a concentration, so the unit should be molar. Okay? Now, we did pH. Now we're going to do pOH. Oh. What was the formula for pH again? pH was equal to negative log of concentration of hydrogen. What do you imagine the formula for pOH is? Negative log of the concentration of hydroxide. Yes? So basically that P means negative log. Yes? So in the example we just did on the previous page, we were given the hydronium ion concentration and we calculated the hydroxide ion concentration, and these were the values that we were given and the value that we got. This is in the same solution. So let us calculate then the pH and the pOH. And because if you have a written response question, you need to write the formula. We're going to do that here. So pH is the negative log of, in this case, I'm going to use H3O+, which is equal to the negative of the log of 3.0 times 10 to the minus 3. And we get 2.5228. To how many decimal places should we give our answer? Two decimal places, because that is our two sig figs. So we're going to then round that to 2.52. Let's do the same calculation, but now for pOH. pOH is the negative of the log of hydroxide. Do you get credit for writing that? Yes. Do you get full credit if you don't write that? No. Okay. So that's now the negative log of, what is it, 3.3 times 10 to the negative 12. And we get 11.48. What do we get if we take 2.52 and we add 11.48? We have 14. 14. So it turns out that as long as you are at 25 degrees Celsius, pH plus pOH gives you 14. And hydroxide ion times hydrogen ion gives you 1 times 10 to the negative 14. Yes? Okay. So we are going to just look at one of these examples. I don't think we're going to go through all of them because I think it's very repetitive. If you would like me to make a video of more of the examples, just send me an email and I will make a video of more of the examples. But we're going to do the first one. So given a hydrogen ion concentration, we're going to be looking for the hydroxide and then the pOH. What formula do you use to get from hydrogen to hydroxide? To get from hydrogen ion concentration to hydroxide, what do we use? Yes, we use the Kw, okay? So we're going to use our Kw, here it is. And we know that it is 1 times 10 to the negative 14. You don't necessarily need to write down this first line. What you would need to write down is this part here, where you have rearranged it to solve for OH. If it helps you to write it down and then solve for it, that's fine, but you don't have to. And you don't have to write this down separately. You can just plug that in, but if it helps you to write it down, please do. So you will plug your values in. Kw is 1 times 10 to the negative 14. H is 5.4 times 10 to the negative 12, and we get this number here. I've kept more digits than I need. Yes? And that, oh, what did I forget? Unit. That should be molar. And because there's like both hydrogen and hydroxide floating about, I'm going to note for myself that this is that concentration of hydroxide. Once we have our hydroxide ion concentration, we can go the second step and find the pOH by taking the negative of the log of hydroxide. So you're going to get credit for writing this bit here. You're going to get credit for then plugging in the value. And then in your final answer, you get credit for not only having the correct answer, but also having it to the correct sig figs. Except for you, you don't have to worry about it. Does anyone feel like they would like to see another example of this, one that's not been pre-written? That's how I felt about it too. Okay. I don't know why I thought it would take so many examples anyway. All right, so we're starting to build a set of converters that will allow us to interconvert between pH, pOH, H, OH, all sorts of things. So we know that pH is the negative log of hydrogen. We know that pOH is the negative log of hydroxide. So does it stand to reason that the pKw is the negative log of Kw? Does that make sense? Because whenever we say P, we just mean take the negative log. Okay? And we know the relationship, Kw is hydrogen times hydroxide, and we know that Kw is 1 times 10 to the negative 14. You know what, we're just going to skip this bit because, again, this is just another example. You can read through it if you want to. Are you interested in knowing the derivation of this formula, or are you just like, that's nice, Miss Spence, I don't really care? Derivation, it's how we get from this to pH plus pOH gives us pKw. You guys sound super excited. Shall we just skip it? Okay. We can come back to it later if anyone's really excited. Basically, you do some logarithm stuff, and it is sort of explained here. You use the log A of B equals log A plus log B. Anyway, blah, 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 blah. Basically, what you end up with is that at 25 degrees Celsius, and I'm going to write it here even though I've written it there, 14 is equal to the pH plus the pOH. The 14 only works at 25 degrees, but at all temperatures, it is true that the pKw is equal to the pH plus the pOH. It's just that pKw will equal a value different than 14 at other temperatures. Anyway, if you're wondering about the whole pKw thing, pKw, that part is actually written here. pKw is the negative log of kW, which is the negative log of 1 times 10 to the negative 14, which gives us 14. And that's where that 14 comes from. Yes, I think that of all of that derivation, probably this is the only real important bit. You can look at the rest of it if you get excited about logs and proving things. I kind of like doing that sort of thing. Like I remember there was a physics test, my second semester physics, and it was something about the electric field around a point charge, which is not particularly complicated, I am given to understand from other people who are smarter at physics than I am, but I derived the formula for the electric field around a point charge using calculus, and I was very excited. And it turned out that all we had to do was write down the formula that we'd been given in class, and we didn't actually have to derive it. But I was so pleased with myself that I'd actually been able to be like, oh, I can do this, and calculus happened. And then I had the formula, and then I used the formula, and I felt so proud of myself. Anyway, so if you're interested in that kind of thing, if you're as big of a science math geek as I am, you can take a look at this, and it is kind of interesting. But what's going to be really important for chemistry, in Chemistry 12, is this handy-dandy little conversion chart. This is taken directly from Hebden on page 138. And what you can see is at the top of the chart, we have the hydronium and the hydroxide. And to interconvert between those two, we use Kw, has those two terms in it. Now, if we want to go from hydronium or hydrogen, remember that this is just the same as hydrogen. We'll use pH is the negative log of hydronium or hydroxide, or not hydroxide, hydrogen. Sorry. So that's going to get us from hydrogen to pH. Going from hydroxide to pOH, we're going to use essentially the same formula, but we replace hydrogen with hydroxide. And the newest one that we've just learned is that if you know pH, then you can find pOH by using pKw. Yes? What is pKw? It's the negative log of Kw. And what's the value of Kw? 1, that needs to look more like a bracket. 1 times 10 to the negative 14. So pKw is 14. Yes? So that's lovely. So I can go from left to right across the top using Kw. I can go from left to right across the bottom using pKw. I can go down using pH is equal to the negative log, and I can go down using pOH is equal to the negative log. What am I missing in my little chart right now? So far, I cannot go which direction? Diagonally, what I'll do is I'll just take a corner. I'll do it in 2 steps. Yeah, so if I have hydronium, I can go to pH and then I can go to pOH. Or if I have hydronium, I can go to hydroxide and then I can go to pOH. What I'm not able to do at this point is go from pH to H. Yes? I can go from H to pH, but I can't at this point go from pH to H. But super easy. Shall we do it? Okay. Okay. When we find a pH, we do the things in the following order. We take the log and then we change its sign. We make it negative. Yes? So to undo this, we're going to have to do the opposite operations. So if we're logging it, we're going to unlog it, which isn't actually called unlogging, it's called anti-logging. Okay? And we're going to do them in the opposite order. So the first thing you're going to do is you're going to change the sign, and then you're going to anti-log it. Now, what is this business, anti-log? Well, if you write the formula this way, it's pretty straightforward. Hydrogen ion concentration is the anti-log of the negative of pH. However, anti-log is simply the inverse of a log. In other words, it is a 10 to the x. Yes? Because if I had pH equals 7, let's just do it with a number that's nice and straightforward, what would my hydrogen ion concentration be? 10 to the negative 7, yes? And if my pH were 3, my hydrogen ion concentration would be 10 to the negative 3. So basically what I'm doing is I'm taking 10 and I'm raising it to the power of the negative of the pH. So this is the formula that I find most of my students prefer. Also because on your calculator you will probably find a 10 to the x button. Yes? And if you cannot find such a thing, let me know. It's usually the second function of the log button. So here's a nice easy one, and this one we're going to look at sig figs as well. We have pH equal to 4.0. So hydrogen is equal to 10 to the negative pH, which is 10 to the negative 4.0. But if we're going to include significant figures, how many sig figs in our pH? 4.0. 1 sig fig. Yes? I actually find people are usually pretty good at finding the decimal, like how many are in the pH, but going backwards, they'll forget. So I'm going to remind you, there's only 1 sig fig here because in pH, the significant figures are after the decimal. And so we need to have 1 sig fig here. Recall, in pH, only digits after the decimal are significant. Therefore, our answer must have 1 sig fig. Okay. So if we have a pH equal to negative 1.00, hydrogen ion then is equal to 10 to the negative pH. So that's negative 1. Yes, that's one of those weird pHs that's negative, okay? Now, 10 to the negative 1 is just 10 to the 1, yes? How am I going to write that with the correct sig figs? First of all, how many sig figs do we need? We need 2 sig figs. 2 sig figs. So 10 to the 1 is going to become something times 10 to the 1. 1.0. 2 sig figs. I wrote this one the other way just to give you an example of how you could show the work another way if you want to. Totally up to you. You can write hydrogen ion or 8 hydronium ion is equal to the antilog of the negative pH, which just means 10 to the negative pH, yes. Same thing, but you can write it this way if you prefer, your choice. So we're going to take the antilog of negative 7.320. Please do that on your calculator and see what you get. You should, hopefully, let me know if you don't, and I'll help you. 4.7863 times 10 to the negative 8. Are we loving my answer? Is the number okay? Number-ish. Number's okay. What's wrong with it, though? Sig figs. How many sig figs? 3. So we need to have 3 sig figs, so that's going to become 4.79 times 10 to the negative 8. Am I done? Units. Concentration, so it is molar. So, anyone having trouble taking their antilog? Let me know if you have any troubles with that at all. So I've just rewritten our chart here. so that you have everything all in one place. It is worthwhile memorizing this chart. Go home and write it out every day between now and Friday, okay? Because you have your quiz on Friday. Yes? Okay, and that's it. And then there's just exercises. So, yeah. So tonight, your homework is to study for your quiz. If you're feeling ready for the quiz, you can do work on 4.2a and 4.2b, whatever you haven't worked on yet, okay?